Okay, good morning, everybody. Oops. Here we go. Okay. Well, let's see. Let's do some what I call the administrative work, but I hope you guys are well. Remember, we got some work to do. I've been doing a lot of work here for this, so let's go. Let's look at the browser here. Let's talk about what we need to talk about, right? We know we're going to go to Math 262, and what we know is we have on scheduled here Monday, May 4th is your test three. Now, I did a few things yesterday for you guys um, and this morning, so let's talk about a couple of things that we did. What I did is sent you guys a reminder of your homework. I did that through Canvas. So I gave you some homework. It's a little bit updated, but there's a few extra problems that people commented about, and I thought they were pretty good to think about and consider. Um, so I gave you guys that reminder that your homework is due. Now remember, your homework is due before your test. So that's the idea. So remember, you want to scan your homework, put it all together. Don't send like 20 different PDF files, right? You want to batch scan that, and then you turn it in the homework portion there, I guess the assignment called homework 3. You turn that in, and I sent the communication to you guys. I also sent communication about the test and how to do things. So your test is gonna time out. The test isn't done when you're done, right? So the test times out, and then after that, you have a short window to turn it in. And again, it's going to be turned in the announcement portion. So you're going to turn in your test. It's going to be completed math 262 test 3, right? So it's going to be our completed test 3. That's where you turn it in the announcement portion, just like you guys did the last time. So everything is the same. It's just that hopefully you guys have the bugs worked out, right? The scanning software, or I'm sorry, app on your phones worked out, and then you turn it in. So keep track of your time. Okay, now some of you guys are going to go the proctorial route, right? You're going to go through, because you have a webcam and a camera, and so I'm going to set that up there for you guys, okay? And after that, some of you who do not, you're going to go through the webcam, non-computer laptop portion to do your test, and you're going to submit your test. And that's that. So if you guys like, I can have you guys start early again, just like last time. I can get that, program there for you so you can start early. Let's see what time our class. You could start at 7 if you like. You get extra 40 minutes. And, that seemed to work well. So I'll set that up this weekend for you. But I also did, if you guys notice here, go way down here, Test 3 study guide. So you have a study guide for Test 3. Now, these are just some questions that I've taken from past exams. Okay, so your real test here, remember, this is an in-class test that's kind of short. It's too short for a calculus class, in my opinion. This is why you have an in-class short version and then a take-home version. And remember, people go, well, the take-home version is longer. Oh, yeah, that's the idea, right? Because the in-class is too short to actually test you. So at least test you in a way I think is thoroughly test you. So, yeah, the in-class is going to be shorter. Take-home is going to be longer. But just take a look here. Some interesting kind of questions for you guys. And I threw that together yesterday. I uploaded that for you from the past. And, yes, it's not going to be as long. So there you guys go. It's kind of a study guide. It's some things that we went through. All right, let's see. What else? Okay, so I think we're good with those things, the announcements. Today, if I go back to our class, right, we got this online transition. I want to remark about a couple of things. Oh, yeah, I'm going to put some extra examples of calculus for parametric equations. I thought I'd get your study guide up first, however, to help you guys out in that way. So I'm going to put some additional examples here, okay, for you guys. And that'll go to the right here. Now, today I have a couple of things here for you guys here. We got polar coordinates here. So to remind you guys, polar coordinates, this is a topic that's studied in trigonometry. And it's very important because you do calculus of polar curves. This system was introduced by Sir Isaac Newton. And he introduced the system to more easily describe curves in the rectangular coordinate system and then consequently perform calculus with those curves. It's an ingenious system. And it involves some concepts in trig, and it's based on two variables. So we need to know two things. R, which is the radius, theta is a central angle, and again, we actually are going to talk about this. It's centered around a pole and a polar axis. So we're going to give you a little bit of review, but I do have some notes here about this I created for you guys. The ideas that are behind plotting points, because you kind of have to know where that starts, right? The definitions, and then know the relationship to the rectangular coordinate system. And so I do have this, and then know that you can convert, and then you have this idea of curves, polar curves that you guys have seen in the past in trigonometry. And of course, you have the famous circles, which are kind of, as you guys can see here, you might be able to guess R is 4, R is -2, R is 1, R, all these different R values, constant. So I have a worksheet here of polar curves based on the past I did for you guys. Lines are going to be important. Cardioids, those hearts, that you study in trig, convex limicons, and all the assorted curves associated with those. These are all, relations, of course, but they're all polar curves that we're going to look at in some detail. And I got some roses here for you guys, all these nice different curves I created for you guys. So I'm not going to go, though, into the details about how to really graph some of these in this course for a couple of reasons, because it's studied in trig, number one. And then the second thing is that, there's a time issue. So that's why you don't go into the details, the intricacies of graphing every one of these kind of things. But they're there. You can read a trig book. I teach it in 241. You can read that trig book and take a look at the details about how to graph polar curves. But this is what we're looking at, okay? So we're going to start today to just kind of discuss the polar coordinates, because we need to know a little bit of those details to start to do the calculus of it. So we're going to look at those details. Now, go back here. Now, this is not going to be on your test. So the first thing people say is, Mr. Judge, is this going to be on test 3? And the answer is no. It's not going to be on test 3. And then I'm going to remark, I was looking at this. I was trying to set up in my iPad notes for polar curves, and it wouldn't let me because it says it was taken. And, it exists already. And I thought, well, yeah, it does. So if you go to my trig page, Math 241, and you go to worksheets and videos, I have a bunch of trigonometry worksheets and videos I started. And then here, I have Intro to Polar Curves here. So there's a video here called the Intro to Polar Curves. I'm going to just turn this volume off. And it's about an hour and 17 minutes long, just looking at this down here. So I have started, ladies and gentlemen, a discussion from trigonometry 2 years ago. And oh my God, I just realized something. Take a look. This only has 1 like. So all this work giving people polar representation of curves has only 1 like. That's heartbreaking. Okay, heartbreaking. Anyway, I go through some details about the polar curves. You guys can look this over for yourself. Again, it's not going to be on this test, but this is some of the work that that I've done in the past regarding that. So you guys can take a look, because I'm not going to go into all this detail. And I might put a link. I might put this up in Canvas for you guys. I'm just going to go over a little bit of the fundamentals so that we can get started on the calculus, because the theory is that you guys had this before and you know about it, okay? So, yeah, take a look at this stuff. 1 like. Wow. Okay. How many views? 64 views. Well, good. We can at least double that now, right? Because you guys may want to take a look at that. So, anyway, let's go back here. Let's get rid of some of these things. And we'll go back to our calculus course. But anyway, that's what's going on. I put a study guide there for you guys. Polar curves are not going to be on your test. But let's try to find those notes. Let's kind of start with some of these here, right? Well, we can put it in the iPad. All right. So here's kind of the idea. Let me start with just reviewing here polar coordinates for you guys. And if I go to the iPad, everything should be there. I don't know why this is always off. Okay. All right, who knows? Okay. We're in the browser now, and we're going to the iPad. And, of course, we go to the iPad. We want to enable that screen mirroring. I'm going to do some screen mirroring. I need a little code here. It's going to come up shortly. 0971. All right, here's our iPad, and then yeah, there we go. All right, that must have been what the reason was. Okay, I had that scrolled. Okay, so if we scroll in a little bit here, all right, you can see what we need to start with. Okay, here's some of our definitions of how we start with the polar curves. So I'm going to remark, you start with a pole. So the pole, ladies and gentlemen, is thought of as kind of like the origin. And then you have this thing called a polar axis that is horizontal. Okay, so this horizontal polar axis right here. Here's where we start. I don't know if I like that. Let's do something like this. Here's your horizontal. It's a ray. This is called the polar axis. So you have two things. You got the pole, you got the polar axis. Now, go back to trig. Generally, when you rotate, we're going to rotate this polar axis, this ray. We're going to rotate this counterclockwise. When you do that, your angle theta here, the central angle, is positive. Just want to remind people, theta is positive when you rotate. And that should be over here. My pad wants to be. There we go. Sorry about that. So you have your pole, you got your polar axis, and you have this counterclockwise rotation. Theta is positive. So if you guys remember, you rotate a ray, counterclockwise direction, that's going to give you a positive angle. And if you guys also remember, the clockwise direction will give theta being a negative angle. So you can rotate that ray in the positive direction and negative direction. That's just counterclockwise versus clockwise. So we're going to rotate that ray. Now you say, okay, is that what you mean by the angle theta here? Yes, we do. So we're going to have an angle theta. So this is a coordinate system, two variables. So we start with the pole and the polar axis. We rotate this either clockwise or counterclockwise. But we are going to also need to know an R value. And you say, what's the R value? Well, R is called a radius value, really. And the radius here, we start by saying the radius is positive, but but you're going to see negative radius values, and I'm going to show you how we define that. So if I go through my notes, a radius can be, if we use these sort of, I should say, these unit marks, radius of 1, radius of 2, radius of 3, radius of 4, radius of 5, radius of 5 maybe, I'm 6, sorry. We can have a radius value, in this case, of 6. That's these dash marks, right? These unit radius values. So you're going to have two values here to work with, a radius and an angle, central angle, and that's going to define a point for us in what we call the polar curves, polar coordinate system. So if I read further, I say these are 2 points. I have my pole here. That's the origin O. This is point P. There's 2 points here that we can see. One at the pole is the origin, and we have an arbitrary point here. So I did talk about the notes down there. And let's look at some facts here about this for a second here, just for a second. If I actually do this, here's my notes from, and I erased them this morning. I erased all the work that I did in 241 a couple of years ago on this. The reason they call this, ladies and gentlemen, polar coordinates is because it's based on a circle, right? So you can have a point here, any point out here. Here's an arbitrary point, and in this case, we can have a radius of 1, 2, 3, 4, and the angle here, since this was trig, is 30 degrees. Now, you could use 30 degrees, or you can use radian. This is pi over 6 now. So we can plot points here. Pole, origin. This is the horizontal polar axis, ladies and gentlemen. And it's thought of as me just simply rotating this ray. If it's positive, that went counterclockwise. So you think, oh, okay, you rotated the ray counterclockwise. You took 1, 2, 3, that 4 radius on this circle, and you rotated this 30 degrees. This is pi over 6 radians, right? This is that location of the point. So we actually can plot points with these two values. This is r for radius, and then our central angle. Remember, central angle comes from the idea of a circle, the center of a circle, and it's here, 30 degrees. So this is how you start to plot points in the polar world. Okay, so you start with the pole at the center. You have this horizontal polar axis. Think of rotating the ray. You really took this point right here, and you rotated it counterclockwise 30 degrees. And this is where we get this polar coordinate system, okay, based on a circle. So let's start with a couple of points we want to plot. Let me erase this here so we have some idea with some explanation. Let's kind of make it uncluttered. What I did in the past here, if I said to you, let's start to plot a couple of points. We're going to plot the coordinates, maybe 3, and I'm going to say pi over 4, and we can call that different letters. I'll say P. We're going to plot Q. How about if we say 2, and we're going to say here, this would be, 2 pi over 3. And then another point, R, we'll say 1, and this point's going to be maybe pi, for example. Okay? Just start to plot some points to dust off the cobwebs here. Right? You have a radius value. That's the first number. You have the central angle. That's the second number. And of course, it's in radians. So for point P, we need 3 pi over 4. So what that would kind of seem like to be 3 pi over 4. Pi over 4, do you guys remember, is actually 45 degrees, right? So if I went out 1, 2, 3 units, I now have to rotate my ray 45 degrees. That's positive, so I go counterclockwise. And as you guys can see, I actually have the graph right here. Here's where 45 degrees would be. So 345 is up here. 1, 2, 3. So here's the location of P. 3 pi over 4. And that's what we labeled P. All right, you guys okay with that? You can see that a bit better. There's our first plot. And then similarly, you might say, well, what's the next one? Well, that's 2 pi over 3, but we got to know what this angle is, right? So if you guys remember, pi over 3, let's see, 2 times 180 divided by 3, isn't that 60? So this is 120 degrees. So if I go back now, and let's redo this, I'm going to get rid of all my marks. In this example, we go 1, 2. That's my radius value. And I rotate to 120 degrees. So I rotate the ray, and I usually use my hand, but not this time. We can't see. Looks like we have here. This is going to be 1, 2. This is our location of Q, which is 2 pi over 3. So here's some angles here. Okay. Now let's look at R. R is going to be 1, and then theta is pi. We know that's 180 degrees. So if we erase everything here, we go to 1. Here's my radius. And then 180 degrees is actually, you guys know we got to go the other side. Well, that's actually the location. So we're going to plot that point here. This is 1 comma pi. And we called that point R. So this is how we start to plot these coordinates in the polar world. But what starts to happen now is we have to ask these questions here. I'm going to have to note, I'm going to have to remind people that we can have negative angles. And when we have negative angles, we have a clockwise rotation here. And this is what I'm saying actually in the notes from the past here. If I get rid of that, this is what I told people. Here's your radius, here's your rotation. We looked at positive angles, now negative angles. And this first example here, let's do these examples, are going to be 2 negative pi over 2. And I labeled it P in that 2 years ago. We can actually do it this way. We can just say, you know what? Let's not even give them letter names. That's something you may give beginning algebra students, but it doesn't matter. It's it's very useful. So let's actually just look at this as the coordinates, r and theta. So in this case, r is 2 and theta is minus pi over 2. So we got to plot these points, 2 minus pi over 2, and let's get rid of those labels. And I'll say, you start by saying go out 1, 2 units, but then we have to go negative pi over 2. That's going to be, if you guys remember, that's negative 90 degrees. So that's a clockwise rotation because your angle's negative. So you're going to go rotate this ray this direction. And then that'll give you a point now. If we can see that, 2 units. I'm actually at the same location again. So this is the address of 2 comma negative pi over 2. So we can see that there, rotating our ray. This is plotting points. And then you say, okay, Mr. Judge, what about plotting points? What about, if we look at another example, what about saying here, how about, do we have, let's say 4 now. Well, let's see, what did I ask them? 4. Oh, 4, isn't that weird? 4. Negative what? 3 pi over 4. Maybe I read that and I remember it subconsciously. Okay, here's a radius. Well, what's the value of negative 3 pi over 4? Well, isn't that negative 3 times 45 degrees? And that's going to be negative, well, 3 times 40 is 120. That's negative 135 degrees. Clockwise rotation again. So I need 4 for a radius. And I go up here and say 1, 2, 3, 4. And then I got to rotate clockwise 135 degrees. Well, this is going to be a little bit interesting here, right? How do we rotate 135 degrees? Well, this is going to be, if I rotate, let me try to do this. This is 90, and this is 180. Oh, that's too much. So if I go clockwise 135, that's 90 plus 45. So here is our rotation of the ray, 90 degrees. Now we have to do another 45. So if you might say, is that 270 minus 45 degrees, right? Can we look at it that way too? We can. So what would that be? If we said, oh, 270 minus an additional 45 degrees. Well, that looks like it's going to be, well, can't do that, sorry. Oops. 5, 2, 225. So we're going to be over here, ladies and gentlemen. So we have to go 4 units now. Remember, this is going to be on this line here. We rotated negative 135 degrees. So we're going to go here to this line. 1, 2, 3, 4, ladies and gentlemen. Here's our point. We're now at 4, comma, negative. Let's do the formal address. negative 3 pi over 4. And that's our location over here. So we're looking at this here, plotting some points, and then I'm gonna say a few other things here about this, some important details that we have to remember for polar coordinates. So maybe it's in my notes. Here's what we're getting at. Let's go back to the facts here. If p equals 0, that means your point is the origin. Then we can say that the radius value is 0, and the location of the origin or the pole has this particular address here. All right, so let's see. This is what we're saying. That when you let r be 0, in general, r theta becomes now 0 theta, and theta is any angle. So the second that you have, I should say, the radius value is 0, you're talking about the pole. However, I do want to remark something about polar coordinates. They're not uniquely defined. This is a very big deal. They're not uniquely defined. And I'm going to say to you guys what that means is, I want you to note that a point r theta is the same as r theta plus 2n pi, where n is an integer value. What that means is exactly what I just said, is that these points are not uniquely defined. And we say here, not well defined. I can show you some examples of what that means. If I said to you, let's go back, and we have the first point that we looked at, 3 pi over 4. Here is the location. If I take this point with the ray here, and I rotate that either clockwise or counterclockwise 360 degrees, I'm at the exact same location again. And it doesn't matter what direction I rotate. If I go 360 clockwise or counterclockwise, if I subtract 360 to the angle, remember this is what we're focusing on, we are adding multiples n of 360, which is 2 pi. It could be positive, it could be negative. This is why we write 2n pi. So 3 pi over 4 plus 2n pi is the exact same point as what you guys see. And this is for n is 0, n is plus or minus 1, plus or minus 2, because those are integer values, right? So they're not uniquely defined, meaning it can have a different address, but it's at the same location because you're going along a circle. All right, you're going along that circle. So this is kind of what we mean. Now, this is applicable, or I'm saying, well, here we go. The origin is also not uniquely defined because theta now can be anything. Let's get rid of this keyboard. Right? Theta could be any value. So the origin can be described as 0 pi or 0 pi over 2 or 0 minus pi over 4. Okay, so that's all they're saying, is that you have many ways to describe the origin. But there's many ways to describe the same point as well, because it's along a circle. So the next thing we want to talk about in terms of the facts here, they're not well defined, or they're not unique, meaning one of a kind. It's not like the Cartesian coordinate system where it is one of a kind. In the polar world, it's not. So anyway, that's kind of an interesting detail. We're going to define a negative radius value. So we're going to have this idea of a negative radius value as being a location that is across the pole. Now, what we mean by across the pole, ladies and gentlemen, here's P, and across the pole, here's the pole. That's across. It's really, if you guys notice, this should measure 180 degrees. So you guys know. So when we really say across the pole, this is what we mean across. It's about 180 degrees difference. So here's the definition, right? I think I wrote that down. We define a negative radius value as being a location that is across the pole that is the points r theta and minus r theta lie across the pole along a line that is the same distance. Okay, here's the key. Here's what I'm saying. This distance here is called r. We have that notated here. And I said here, r is positive in this situation. But being across the pole now, this distance is the same as this distance. This distance in absolute value is the same. So remember, we're looking at calling that the absolute value of r, but we define r here to be negative. So remember, the absolute value of minus r will be r, so that's all they're saying. It has the same radius value. It's the same radius value, ladies and gentlemen, but it's just across the pole, 180 degrees difference. And that's what they're talking about. So let me do this now. And you say, okay, how do we apply a negative radius to our picture here? Well, what did I put here? We got a bunch of other examples. Oh, this is what I already talked about. This is, they're not well defined. This is the definition I gave you guys. Negative radius value. Let's try this. Negative 3 pi over 4. So my radius value now is negative. Remember, pi over 4, that's counterclockwise rotation. So I can go back up at, and it probably is a good idea, negative 3 pi over 4 to go back up at this picture. And I'm thinking now, ladies and gentlemen, I want to erase a lot of this stuff because it's cluttered. But you can watch the video. Negative 3 pi over 4. So remember, we're going to plot that. So you might say, how do we start to look at that? Well, plot it this way. Look at it this way. Do the positive angle first. You say positive. Yeah, you might want to plot first. Let me change the colors. Try plotting 3 pi over 4. This is what I do. I go out 1, 2, 3. I rotate that pi over 4, that ray. Here we go. Here's 3 pi over 4. That's not what we're looking for. And I used to do this with my hand on the whiteboard. Every math instructor has, meaning I put a portion of my hand along this line here. And I remark to students here, if I go along this line, here's that line. I can't do it. I can't show you guys. You can't see me, but you guys can see that across the pole now. Remember, this measures 180 degrees. That's across the pole. I can now label this as 1, 2, 3 here. This is the location of negative 3 pi over 4. This is what they mean by across the pole. Okay? So this is our location. This is how we handle negative radius values. Let's write that negative 3 a little better. So there you guys are. There it is. So we can even try another example. I guess, what did I say out here? Back in the trig days, negative 1 pi. Let's try another one where negative 1 pi would be. Negative 1 pi, we start with the positive 1 pi. I'll put that in blue. So here's positive 1. Pi would be, that pi is over here. So I'm over here. This is going to be really the location of 1 pi. However, you say we want to plot negative 1 pi. Well, negative 1 pi, you guys know, is across the pole, an equal distance. Here's negative 1 pi. I know, these points are not well defined. So across the pole, 80 degrees difference is the location of, so we got 1 pi here, negative 1 pi is across the pole. Let's try one more. You say, okay, what about, for example, they want us to plot negative 4. Let's try that, negative 4. Negative 4, we're going to say pi over 6, and that's really negative 4, 30 degrees. So you start, ladies and gentlemen, by plotting positive 4, 30 degrees, and you say, where is this? This is 1, 2, 3, 4. We rotate 30 degrees. Here's positive 4, pi over 6, 30 degrees. Now, across the pole will be, in the other direction. 1, 2, 3, 4. Negative 4, pi over 6. This is across the pole. So I want you to compare 4 pi over 6, and now that's negative 4 pi over 6. Starting to get a bit cluttered. Let's erase some of this. Now I'm going to put a couple of things together here. Put a couple of ideas together, and that's just going to be to say what happens when you do both. So I'm gonna change some of these notes here. I'm going to give you some of these other examples. I'm going to do let's look at some points. Let's change the color on that. How about if we say negative 3, negative pi over 4? What happens when you have a negative radius value and also a negative angle? Well, negative angles, you guys know, that's going to be, negative 45 degrees, and that's counterclockwise. So you do it the same way, meaning you start with 3, a positive value, and you say, isn't that negative 45 degrees? Okay. So let's see how that looks. We start with the positive radius, 1, 2, 3, and then we go 45 degrees down. Well, that's negative, right? So that's going to be clockwise. So I go 45 degrees will give me at 3. Let's double check. I can't see there. Okay, there we go. That's 3. Let's change that. Maybe we should put that in blue. That's 3, negative pi over 4, because we rotate the ray clockwise. What is opposite the pole? Let's be careful. Has to be along that same line, and it is. So it has to be 1, 2, 3 units. And it is very annoying that the iPad automatically goes to the eraser. And that's negative 3, negative pi over 4 here. So here's a location and how we actually handle both a negative radius and a negative angle. And this is just plotting points. And then you might say to me, well, okay, I remember plotting points. We also have this idea of conversion. What I wrote in our notes here is that every point in the Cartesian coordinate system can be represented on the polar coordinate system as we superimpose both systems on top of each other. So here's where we start to get some nice, interesting definitions. Now that you guys know how to plot a few points, here's what I'm saying to you, that the location r theta, if I put my polar axis along the positive, what we say, the polar axis along the positive x coordinate axis. This is also thought of as being x, the x-axis. We can actually see that the pole is at the origin, the location 0, 0. And actually, we see a lot more than that. Okay, we can go back and use some definitions of sines and cosines from geometry. Meaning, excuse me, we can start to define a few things. That sine theta, we know by definition, is opposite over hypotenuse. Well, that makes that y over r. We know cosine theta is adjacent over hypotenuse, which is x over r. So we superimpose this. This distance down here, though, is they're calling this distance, it's weird, x. This is this whole distance. And then they're going to call this distance over here y. And that's the location of your xy coordinate there, the point that we call P. And they're using some right angle trigonometry or geometry. You guys notice this is my radius. And remember I said right angle, that's a right angle. We're getting these definitions of sines and cosines. And they simply solve these here for y and they solve these here for x using algebra. And that's why you get this x is r cosine theta, x is r sine theta formula. But then you say, Mr. Judge, where'd they get this other formula here, x squared plus y squared equals r squared? Well, because you have a right triangle. Here's x, here's y, here's r, here's your 90-degree angle, and by Pythagorean theorem, you get x squared plus y squared is r squared. Similarly, we can get tangent theta. You say, what's tangent theta? Well, if I look at this again, I'll get tangent theta is y over x, because the definition is opposite over adjacent. And of course, x can't be 0 here. So you have some nice definitions that you get when you just superimpose the Cartesian coordinate system with the polar coordinate system, put them on top of each other, put your pole over the origin, and we now have a way to, ladies and gentlemen, convert, go back and forth. So there's a conversion process. We can convert points. I believe, and this goes here, we can convert. So I'm going to write down here, we can convert to the different systems. You can go back and forth. You can convert from polar to rectangular, rectangular to polar. And maybe I should remark about this conversion idea. Let's do a couple of conversions here. I know this is review. Let's see in my notes what I did years ago, even though I erased all of these. Oh, we don't have that. Okay, let's convert then. Give you a couple of conversions. So r theta to xy, this is converting polar to rectangular. We can go back and forth. If, for example, they give you 3 comma power 4, you're gonna convert. This is polar. Here's my radius. Here's my angle. You might say, if I do that, what do I use? Use x is r cosine theta, and y is r sine theta. Very simply, you plug in 3 for the radius, and you plug in power 4 for the angle. If you guys remember these here. So you get x will be 3 cosine power 4 You get y is going to be 3 sine pi over 4. Now, these are 45 degrees. You guys know what these are. This is going to be 1 over the square root of 2 or 2 over the square root of 2, right? If you rationalize the denominator. So you get here, the x-coordinate is 3 over square root of 2, and the y-coordinate is 3 over square root of 2. So we can say 3 over the square root of 2, 3 over the square root of 2, and if you rationalize, that's 3 square root of 2 over 2, 3 square root of 2 over 2. So let's double check here, see if I'm good, if I made any mistakes. I think I'm okay. Switch to green tea from coffee. Maybe that's going to help. R theta to xy. So this is your x-coordinate. It's your y-coordinate. And that should make sense if I say 3 pi over 4. If I said to you guys, let's take a look. Here's the pole. Here's my polar axis. In fact, I like to do it this way. If I said 1, 2, 3, and I rotate that pi over 4, that looks like this is the location of 3 pi over 4. However, it's also the location of 3 square root of 2 over 2 and 3 square root of 2 over 2. So these are the same points, but in different systems. So we converted. Anyway, it's kind of a little sketch there for you guys. So, you know, your book has some review of conversion of some of these. If you guys like, let's go the other direction. Rectangular. This is just a little quick review. Very, very quick. Let's do the other way. So you say, if I can I convert the other way from xy to r theta? The answer is yes. Convert from xy to r theta. And if you said, for example, let's get some points here. How about if they want us to convert 1, -1? Again, this is Cartesian coordinates. They're giving us Cartesian. Rectangular. And then you say, well, what do we use? Well, you use the other set, right? And if you look at my notes here, we have the Pythagorean theorem and the definition of tangent. And that's from rectangular to polar. So you might write that down and say, I have x squared plus y squared is r squared. And then I have tangent theta is y over x. So when you plug things in, x is 1, y is -1, -1 and 1. Let's see what we get here. We should get 1 squared plus -1 squared is r squared. Or you get 1 plus 1 is r squared. R squared will be 2. And I get r here is plus or minus square root of 2. Interesting. Let's think about that. Tangent theta is -1 over 1, which means tangent theta is actually -1, right? So then if I ask you guys, what is theta here, right? Well, theta is going to be, how do we get theta? Anybody know what theta is? I don't know. What's theta here? When do we get tangent being -1? Anybody know? Tangent's -1 when what happens? Here's my address. Remember the definition? Y is going to be -1 and x is 1. So we go y is -1, x is 1. Where's theta? Y is what? X is 1. Y is -1. Is that right? So here's x is 1, y is -1. Here's how we can think of this angle, right? What angle do we get there? What's theta? Isn't that -π/4? Let's write it down. We got -π/4. And what's the other angle? Right? Isn't this here 45 degrees? It's -π/4. But if we go the other way, what would that be? Isn't that 7π/4? So I have two answers here. All right. Thank you. Thank you. I'm glad we're awake. Just checking. Okay. But here is what I'm going to say now. What do we do with this information here? So what are you going to do with all this information? You got two radius values. And then you have two angles. Right? Which radius do I use? Which angle do I use? This goes back to everything we discussed earlier, just so you guys know. Looking at these points here, this goes back to what we discussed. And if you said to me, well, okay, here's what I want to say. Go back to this picture here, right? What we know they gave us is the Cartesian coordinate location. It's right here. It's 1, -1. That's the P they're talking about. How do I describe this in terms of the polar world? A pole and the polar axis, we got this ray. How do we do that? Well, I could do it two ways. Remember, our points are not unique. They're not well defined, meaning you can have multiple addresses be the same location. That's kind of weird for us, but it's because this is along a circle. Okay, and so let's kind of remark and say, well, I can think of two things. If I go out 1 unit, is that 1 unit? Oh, square root of 2 units, sorry. If I go out a positive square root of 2 units, that's going to be something like, okay, positive square root of 2 units, and I rotate with a negative angle. Here's what I'm saying. That location has a distance, a radius of positive square root of 2, but the angle is negative because I went in the clockwise direction. I can say my radius is a square root of 2, but I have to have a negative angle, -π/4. That's the location. That's one way of doing this. And so, yeah, that distance down here, it didn't look. This whole distance is the square root of 2 from the origin or the pole to that location. That distance is a little bit more than 1, remember? But we went in the clockwise direction. So that's why the angle is negative. So I can describe this location this way. I can also say, what if you said, Mr. Judge, I want to use a negative radius value because I got two values. One's positive and the other's negative. You can do that. But if your radius is negative, what angle do I use now? you might say, if I used the 7 pi over 4 angle, rotate this 7 pi over 4. That's a positive angle. This was in the counterclockwise direction. So if I rotate that 7 pi over 4, it is certainly true that this distance from here to here is supposed to be the square root of 2 as well. We're not talking about this point here at all. We're talking about this point because this is where this location is. This is an x and y value, 1, negative 1. So if my distance here is positive across the pole, I can now use the negative radius here. This is the point. So if you can use the positive angle, in this case, your radius has to be negative. Okay, so these are the things that you discover or talk about in courses like trig. You went through this already. You guys went through the, I should say, the idea of what? Converting points and plotting points. Okay, and I'm going to put a link. I'm going to put this in Canvas. I'm going to put this in the module, the link to that exercise of the lecture that I did for trig 2 years ago. So you can review with that. We got some good information there. But you might say, well, this is calculus 2. We know that stuff. Well, what you want to remember from the polar world is we can describe curves with r as a function of theta. Curves can be described this way. The first things you may want to think about is a family of curves. I mean, I guess I can say this. We can start with maybe the lines and then go to the circles, right? Lines are represented a couple of ways where theta is a constant. That means if they give you any angle, like if they say theta here is pi over 3, there's a couple of ways I can say this to you guys. R theta, if we plot this, this is r, this is pi over 3. This is any r, any radius. And that includes r being 0. So what you're looking at here isn't going to be a line through the origin. I can show you this, how I think of it. I can say, okay, here's my pole. Here's a polar axis. I actually draw the Cartesian coordinate system on top all the time because it helps me with my angles. Pi over 3 is 60 degrees. So I know this is 60 degrees. So I know I have points along a 60-degree line here. This is theta is pi over 3. Any radius value. That includes radius is 0, radius is 1, radius is 2, radius is 3, radius is negative across negative 1, negative 2, negative 3. So what you're looking at really is for any radius value, because the radius is a real number, you're looking at a line through the origin. So we need to know these kind of things. So I just want to remark there's a line through the origin. If they even gave you theta being negative pi over 4, you could do the same thing. Okay, any radius, but the angle has to be negative pi over 4 for all r. Even r is 0, meaning the pole. So this goes through the origin. I just have to remember where is negative pi over 4. This is why I draw my Cartesian coordinate system. And I can say that line is actually negative pi over 4. And what else is going on here? So you guys know, line is negative pi over 4. Any radius. Radius is 0. Radius is 1. Radius is 2. Radius is 3. Radius is negative 1. Negative 2. Negative 3 across the pole. Any r. So what you guys are seeing here is another line. and it's going through the pole, going through the origin. That's what really happens when theta is actually constant. Now, there's different ways we can define lines here. There's a lot of different ways we can do that. That's back in a trig course. The other most important thing I should say to us that's going to be important is circles. Circles happen when your radius is equal to a constant. And we can show you why, right? So if you say, let's let R be 2. Why is this a circle? Well, this is a circle, ladies and gentlemen, because we can do the following, right? I can square both sides. And that gives me R squared here is 4, if I square both sides. You can replace R squared with X squared plus Y squared, which really means you get X squared plus Y squared is 4. This is the equation of a circle centered at the origin with radius value of 2. So that's like a radius value. This is one way to think about it. You can also think about it the way I looked at. You can say R theta. R is a constant to theta is any angle. So this is for all theta. So you got your pole, polar axis, Cartesian coordinate system superimposed. My radius is 1, 2, right here, and it's good for any angle, all theta. So I can plot that radius 2 for any theta, and if you said here's a pi over 4 angle, well, guess what? If I rotate that, here's a point. In fact, I could do it for any angle, even 90 degrees, even 180, 270, all these radius values of 2. My sketches aren't beautiful. Ladies and gentlemen, you get a circle. Radius is 2. And by the way, I've been told that let's get rid of the if we can. I've been told that actually your iPads can actually draw circles, which is good for me. It's undo anyway. You can think of it this way. You can think of it either way. So what I did for you guys, if we look at this worksheet here, polar curves, R equals alpha theta, and actually even relations. These are circles. I gave you guys R as constants here. So you can see for all of these values, I do have different circles, even if the radius is negative, because if you square it, it's positive, right? So all these colors are associated with your circles that you guys see here. And these are also circles. R is A cosine theta, R is A sine theta. These are also circles, and you can prove that. I can show that. And typically in a trig class, you do. And then you say to people, okay, what about this? Theta is constant. Well, this program it's very sophisticated, but believe it or not, whoever wrote it, I would remark to them, I'd criticize them and say, you guys have to allow theta to be constant, because to have to rewrite this as a, implicitly, it's a little bit, it's discouraging. So I can see lines through the origin here. Here's lines, though, that are not through the origin. And you can actually prove those as well. It could be proven, it could be shown. And then here's some of my favorites, the cardioids, the hearts. Okay, you have vertical and horizontal, different colors. Here's the horizontal cardioids. Examples, we're going to be working with these. Convex limicons, kind of looks like an eyeball, really. Cross section of an eye. Anyway, you have a vertical and horizontal. Dimpled. They got some dimples. and vertical, horizontal. You got some loops, inner loops. There's definitions, vertical, horizontal, and you got roses. So you got the 4-leaf roses, and then we have the rotated 4-leaf roses, and then we have the 3-leaf roses. Both rotated. Finally, we have the lemniscates, figure 8 curves, vertical and horizontal. So what I'm going to say to you guys is you don't have to know how to graph these personally. I mean, you do. I assume you do. I assume you know. But I'm not going to test you guys on graphing these. I do that in a trig course. I go through the details there, how to graph it by hand. In this course, we just use the curves. So what I'm going to focus on next time is just the calculus of curves. I'll send you maybe some homework on this section, but it's not due Monday because you're not going to have a test on this stuff. And I went through all the information about the test. So hopefully you guys can review that. And I'm going to say to you guys, if you have any other questions, again, see me during office hours. Again, I'll post the additional examples for calculus for parametric equations, not polar. And then after our test on Tuesday, we'll start the calculus of polar. But I wanted to introduce to you some fundamental ideas first, the setting about things, so that it makes a lot more sense when we start to do the calculus of it. Well, I don't know. Maybe I could look at the book, and I won't. I'll do that a bit later. So take it easy. Have a good day. Be prepared. Remember, make sure you guys know how to upload, where to upload, and keep track of your time during your test. All right? So stay safe, take it easy, and have a great day. See me in office hours if there's questions.